All right, today we're going to look past those shiny panels you see on the roof and uncover the real heart of a solar power system. It's the magic box that does pretty much all the heavy lifting, and we're about to crack it open and see what's inside. So, let me start by asking you a question. When you think about a solar setup, what's the first thing that pops into your head? For almost everyone, it's the panels, right? But are they really the most important part of the whole system? Well, the answer might surprise you. I mean, obviously you need the panels to capture the sunlight, but the real star of the show, the component that's actually doing all the hard work, it's something else entirely. We're talking about the inverter. Think of it as the master translator, the traffic cop, and basically the brains of the entire operation. Seriously, without one of these, all that power your panels are generating would be completely useless to your home. Okay, so here's its main job in a nutshell. A solar inverter is this electronic device that solves a huge problem. Your solar panels, they produce one language of electricity. That's direct current, or DC. But your house and the entire power grid, they speak a completely different language, alternating current, or AC. So what's the big difference? Well, DC power, it flows in just one steady direction. Simple enough. But our entire electrical infrastructure, thanks to that whole historic war of the currents between Edison and Tesla, it runs on AC, which is constantly flipping its direction back and forth. The inverter is the essential bridge that connects those two worlds. But its job is so much more than just being a simple translator. A modern inverter is a multitasking genius. It's juggling several absolutely critical jobs all at once to keep your system safe, efficient, and pumping out as much power as possible. Okay, so these are the four main jobs we're going to break down. First up, you've got its core function, inversion, which we just talked about. Then there's something called maximum power point tracking, which is a fancy way of saying it squeezes every last drop of juice from your panels. After that, we'll get into its super important role in grid safety. And finally, integration, how this whole thing gets packaged together. So how does it actually do that first job, the inversion part? Well, at its core, there's this really clever circuit made of super fast switches, often called an H-bridge. These little switches are just flipping the DC power back and forth thousands of times a second, essentially chopping it up to create something that looks and acts like an AC wave. And that brings us to its next big job. See, the amount of power a solar panel can make is a constantly moving target. It changes all day long with the angle of the sun, a passing cloud, even the temperature. So how on earth does the inverter keep up with all that? This is where the whole brains thing really comes into play. It uses a process called maximum power point tracking, or just MPPT for short. The inverter is constantly, and I mean constantly, analyzing the panel's output, looking at the voltage and the current to find that perfect sweet spot that pulls the absolute maximum amount of power at any given second. All right, now for its crucial safety role. Think about it. If the power goes out on your street, the very last thing you want is your solar system pushing electricity back onto the grid. That would be incredibly dangerous for utility workers trying to fix the problem. So inverters are required by law to detect a grid failure and shut down with unbelievable speed. We're talking fractions of a second, as you can see right here. It's a feature called anti-islanding. And last but not least, there's integration. A modern inverter isn't just a simple circuit board in a metal box. No way. It's a complete, rugged package that's built to survive for decades out in the elements. It brings together the power electronics, sophisticated cooling systems, electrical filters, and all the necessary safety switches into one tough unit. So, now that we know what it does, let's see how it does it. Let's metaphorically crack open that magic box and take a look at the actual hardware that makes all this stuff possible. Okay, deep inside the inverter, you find the real workhorses, solid-state switches. These are the little guys that are doing all that high-speed flipping of electricity we talked about. And they come in all shapes and sizes, from these tiny little switches for a home system to absolute monsters like the one on the left for giant utility-scale solar farms. So after those switches create that rough, kind of choppy electrical wave, it needs to be smoothed out. And that's the job of these magnetic components called inductors. They basically filter the electrical signal, turning it into the clean, smooth sine wave that your appliances need to run properly. And just look at the size difference here with the coffee mug for scale. It really shows you how much more power a big commercial inverter is handling. The other key players in there are capacitors. The best way to think of them is like filters and shock absorbers, but for electricity. They sit on the DC side coming from the panels, and they smooth out any ripples or electrical noise to make sure the inverter has a perfectly clean, stable supply of power to work with. Now, let's get into how engineers deal with the two biggest enemies of any electronic device, waste heat and efficiency loss. Because honestly, getting this right is what separates a good inverter from a truly great one. In the solar world, a number that looks this small is actually a huge deal. It might not look like much, but trust me, that 1% represents an incredible amount of engineering and a lot of money. Here's exactly why it matters so much. If you have a big solar installation, just a 1% improvement in your inverter's efficiency means you can get the same amount of power with fewer solar panels. And that translates directly into thousands of dollars of savings right up front on what is easily the most expensive part of the whole system. And check this out. This thermal image is a brilliant illustration of how they manage that efficiency. Because inefficiency creates heat, designers have gotten really clever. They create separate temperature zones inside the box. All the sensitive electronics are kept in a nice, cool zone, while the tougher magnetic parts are allowed to run much hotter. This simple trick dramatically extends the life of the whole unit. And of course, the thing that ties all this amazing hardware together is the software. This little board, a digital signal processor, or DSP, is the orchestra conductor. It runs unbelievably complex code, developed over years and years, that coordinates everything from the switching speed to the power tracking to all the safety checks, making sure it all works in perfect harmony. So to wrap things up, it's really important to know that inverters are not a one-size-fits-all kind of deal. They come in a few different flavors, or what engineers call topologies, and each one has its own set of strengths and weaknesses. For the systems you see on homes, the two main designs come down to a classic trade-off. The older design uses a big, heavy transformer that is super simple and bulletproof. The newer, high-frequency design uses more complex electronics and a much smaller transformer, which makes it lighter and way more flexible with different solar panel setups. So really, it's a choice between heavy iron and copper versus lighter, smarter silicon. And all this leaves us with one final thought to chew on. The inverter is already the brain of every solar system out there. But as our electrical grid gets smarter with things like electric vehicles, home batteries, and smart appliances, could this humble little box evolve to become the central conductor for your entire home's energy ecosystem? It's a pretty fascinating question for the future, isn't it?